we're working through each component of the refrigeration cycle system. And of course, the objective is to transfer heat from a cold space to a hot space. We've covered the compressor analysis, the condenser analysis, and now we're going to talk about the expansion valve. But before we go to the slides, I'd like to give you a little show and tell about sort of some valve basics in the first place. This is a ball valve. Okay, here's a ball valve. And so this ball valve right now is in the wide open position. So you can see clear through this valve. So you can see that there's very little resistance to flow in the wide open position. And so flow, very little resistance. So essentially the inlet pressure and the outlet pressure of this valve would be about the same. But what happens when I start closing this valve? So the purpose of a valve is to throttle the flow. And so do you see that? So it's working pretty good. So do you see that I've closed the valve a little bit? And so do you see that the effective area of the valve, the flow area of the valve is really reduced in this partial, okay, in this partial valve opening. And so there'd be more pressure drop through there, wouldn't it? So if this is the inlet, the pressure would be high, and coming out here, the pressure would be lower in this partial position. Okay, that's what we call a valve, a throttling valve. A ball valve is a throttling valve. It throttles the flow. It enables us engineers and operations people to adjust the mass flow rate going through a valve at the expense of pressure drop. So now one thing I'm going to do is I'm just about going to close the valve off. And now as you look, do you see that it looks like, at least on the camera, that the valve is almost closed. But if I stick my eye in there, I can see that there's the tiniest little bit, there's the tiniest little sliver of light that you can see going through there. You just have to trust me. You can see a tiny little sliver of light, and that means at the nearly closed position, you get a lot of throttling, right? So the mass flow rate is going to be much lower than the wide open position. It's a throttling valve. And also the pressure drop is going to be a lot of pressure drop. So if we're coming in here at let's say P3, and we're coming out here at P4. P4 is going to be much lower than P3, but also the mass flow rate is going to be dramatically reduced than from the wide open position. And so I do the little show, and so you get the idea that the smaller the effective opening of the valve, so the smaller the opening, the higher the pressure drop, and the more restricted, the more throttled the flow is. Okay, so there was the there's the wide open valve, no throttling, compared to almost shut, lots of throttling, high pressure drop. That might kind of get you set up for your upcoming fluid mechanics class as well. But let's go ahead and do the analysis. Now, so back to refrigeration cycle, let's do the analysis of the expansion valve. Okay, and so this is called expansion valve basics. And the result of here is just elegant and beautiful. So hang in with me here. Let's go back to our refrigeration cycle. Here's our basic sketch. So we're going to be looking at analyzing this expansion valve where we're coming out of the condenser as saturated liquid at a pretty high pressure, P3. And we're going through this expansion or throttling valve, okay, down to P4, a much lower pressure. Okay, so that's the idea. So let's just look at the basics. Let's go all the way back to chapter 4 and see what our first law looks like for our analysis. It's as simple as that. Okay, so I'm hoping that my show and tell gave you the idea well, let's see. Is this throttling valve lifting a weight? No, of course not. Is there a shaft protruding from the valve that's rotating at a steady torque? Of course not. And so you know that there's no power associated with this throttling valve. So on the TS diagram, we're coming in at our high pressure saturated liquid, okay, and we're dropping the pressure down to P4 or P1 into the evaporator. So I hope I've convinced you. So we're going to look a little more at this dashed line. I hope I've convinced you that when you drop a pressure in an open system and you don't get any work out, you don't get any output power, that's extraordinarily irreversible. Okay. Oh, another thing I should say is that we're going to consider this expansion valve, this throttling valve, to be fully insulated. No heat transfer allowed between the valve and the surroundings. So no heat transfer. And also you're seeing that I hope I've convinced you no work, no output power. So therefore, this process, this throttling process, expansion valve process, very irreversible. And that's why we must depict it as a dashed line, because it's irreversible. That's critical. So in your sketching of the expansion valve process, you must show that as a dashed line to depict irreversible. So that's not just a subtle point. That's a very important point to make for you as a practicing engineer. Dashed line for an irreversible process. Well, what does an expansion valve look like? I just showed you a ball valve that an operator or an engineer can manually change the effective opening of the valve. Well, the expansion valve of a refrigeration process is different. It's totally automated. There's no operator, there's no person adjusting the size. And so physically, this is what an expansion valve looks like. If you sort of nose around in a whole house air conditioning unit, you can find this expansion valve, a sort of brass looking thing. But here, this cutaway view is a great way to visualize what the inside of an expansion valve looks like. We've got high pressure saturated liquid coming into this L from the condenser. Notice here how in the cutaway view, what we're trying to see is that on this valve, the effective opening as it makes this right-hand turn, the effective opening is tiny, is small diameter opening right here. I call that an orifice. There's basically an orifice there, okay? And then outlet is going to the evaporator, and that's going to turn out to be a saturated mixture. Okay, so that's critical to sort of see with your eyes what an expansion valve looks like. Okay, let's see what down here in this image. I haven't looked at it in a while, but here, sure enough, I see this little cartoon says we've got high pressure, and it says and hot, so it's kind of colored red. Refrigerant coming into the expansion valve. Okay, it's going through this tiny orifice, so a lot of pressure drop, big pressure drop. So the pressure drops, and it does turn out that this refrigerant is going to get real cold. It's going to become a saturated mixture of vapor and liquid at a low temperature. It's going to be under the dome. So I hope that gives you a better sort of idea of what the expansion valve looks like and how it works. Basically, no moving parts, okay? And that's the idea. And so I hope that this cutaway view has given you the idea of an orifice, very small diameter hole, and that's what's causing the pressure to drop from P3, high pressure, down to P4, low pressure. Big restriction in the line. The flow is throttled. There is an alternative to the expansion valve, and that's called a capillary tube. And it all depends on the application. And this would be sort of for smaller applications of, say, refrigerators, smaller units that are smaller than industrial size refrigeration units, or even whole house whole house air conditioning system. So a capillary tube. But the idea here is, again, a very small diameter. So a capillary tube is simply a small tube that's in between two sort of piping systems that are bigger pipe diameters. The capillary tube, just remember, small diameter. This is a pretty good look at what you've got here is you've got a saturated liquid. Here it says subcooled liquid. Saturated liquid at a very high pressure, a capillary tube or a restriction in the line, very small diameter, and that's what causes the flow pressure to drop, showing 278 pounds down to 70 pounds, and that's what causes the refrigerant, the phase change substance of the refrigerant, to get very, very cold. The pressure drop, the throttling process, and let's see how come that works. I think that covers that slide, and keyword throttling the refrigerant flow, dropping the pressure, keyword adiabatically. So we consider that this area, this capillary tube, fully insulated from the surroundings. What does a capillary tube look like in the real world? This is what a capillary tube looks like. And here's a reminder, if this is picked off from a TS diagram, I'm going to show a dashed line, which is a very irreversible process, a throttling process from inlet to outlet. Okay, so recognize the capillary tube diameter much, much smaller than the refrigerant tubing diameter. That's the key takeaway. What would your sketch look like? Well, it's a reprise of Chapter 4. Your sketch would look like going into this valve. Okay, so it looks like a bow tie. That's a good way to depict a valve, by the way. A little bow tie. You get the idea that there's a restriction in the line. See how the bow tie kind of necks down to a small, tiny diameter? That's a good way to depict it. Much better than a box or a cloud. Okay, coming in at state 3, outlet at state 4. Let's see. I've got an open system, steady state, steady flow, one inlet, one outlet. There's my dash control surface. In my sketch, I'm showing Q dot N equals 0. It's adiabatic. I'm showing that W dot out equals 0. It's not lifting a weight. This valve is not lifting a weight. I'm showing that P3 is much, much bigger than P4. I'm reminding myself that in the textbook, little qn is Q dot over M dot. Okay, so we can write the first law in terms of little intensive values. Little qn minus little W out equals H4 minus H3. And in the absence of potential and kinetic energy changes, which we nearly always consider modeling, very, very little change in kinetic or potential energies. Let's see, what do we get? What does our first law become when we simplify it? We strike out Qn, adiabatic. We strike out W out. No work being done. So the neat expression of the first law for this throttling process, this expansion valve process, is H3 equals H4, constant enthalpy. Man, what a gift, right? So, boy, if you can get H3, and we remind ourselves, how did we get H3? We remember that state 3, the phase, was saturated liquid. Typically, we know what P3 is, so H3 becomes very easy to look up in the back of the book, thermodynamic tables. H3 is pretty easy, and so H4 equals H3. Wow. And let me go back a little bit. Something just came in my mind, and then we'll do the recap. I'm going to go backwards. I'm going to keep going backwards until I get to a TS diagram. There we go. That was a point that I don't think I made in a slide, but I can do it in words. Let's look at our process 3 to 4. And we just showed by the first law that H4 equals H3. Okay, so now looking ahead to the next video of evaporator analysis, you see that the evaporator analysis, it's going to be pretty easy. And you know where we're headed on the evaporator analysis. But what if on a quiz or a test, someone asks you, what is X4? So you see that X4, the quality at state 4, is somewhere between 0, your saturated liquid, and X equals 1, saturated vapor. So there is some value for X4. How would you determine X4? Well, let's see. You know what? You've got a numerical value for H4, don't you? It's H3. If you've got H4, do you see that you could look up H sub G and H sub F, and you could solve for X4 using the definition of quality? That's a very powerful tool, and it's a very likely question on a quiz or test. So I'm gonna go back forward. That's a point that I thought it would be worthy to make here. And what made that so easy? What made that so easy was the statement of the first law for the expansion valve for a refrigeration process, H3 equals H4. So do you see that H3 equals H4 is a statement of the first law? It's not a formula. It's not just a formula you put down on your formula sheet. You can get to this statement, H3 equals H4, very quickly by thinking about what you already know and have mastered about the first law for steady state, steady flow, open system, one inlet, one outlet, and then the modeling of our component. No heat transfer, adiabatic, and certainly no output power. Pretty cool. Okay, a recap. Recap is that the expansion valve is a throttling valve, similar to a plain old valve. It's an insulated, very irreversible process because we're not getting any work out. A lot of people then, practicing engineers, will call it a constant enthalpy process. And that is quite true as long as there's no change in kinetic energy. And what's the purpose of the expansion valve in the refrigeration cycle? It transforms hot saturated liquid at a high pressure into a cold saturated mixture at a lower pressure. So those are the keys. Those are the key things about analyzing the expansion valve. And now I hope that you have a better physical feel for what the expansion valve is all about. And now when I replay the tapes about myself as a younger person and I talk about really not understanding what my dad was explaining to me about refrigeration, I think it was all about my poor understanding of how expansion valves worked. That was a key missing link in my understanding. So I hope that helps, and I hope that helps you understand some of the basics about throttling flow, a throttling valve, and how that relates to the expansion valve in the refrigeration cycle process.